Hello, in this video we're going to test a dose escalation problem using Follmann's test. Now realistically it's called a simple ordering, and dose escalation may be one approach that could be used in this setting. Now I just did another video where I said we're going to look at testing all treatments against the control arm using Follmann's test. I'd actually recommend you going back and looking at that, and that's what's called a simple tree ordering, where this is just a simple ordering. So we're going to develop the necessary equations for this test. So let's let xij be independent, identically distributed, normal, mu I, common variance sigma squared, where I denotes the treatment and j denotes the sample size within each treatment. And so it goes, there's k treatments and the sample size 1 to n. And again, the hypothesis we want to test is h naught versus h1 minus h naught, where h1 is this simple ordering. We've stated it like this because then usually you have to say at least one component strict inequality. But if you just exclude the possibility of all equal in the alternative hypothesis, then that's equivalent. But what we want to do is develop an equivalent set of hypotheses so we can use Follmann's test to test this. So we want to develop an equivalent set of hypotheses. So let's let the vector v be the mean differences. So 2 minus 1, 3 minus 2, all the way up to k minus 1. Then this is an equivalent set of hypotheses. So if each component in here is 0, then that's saying all the means are equal. And if all these are positive, that says that there's we're in this setting that the latter mean has to be greater than the previous mean, right? So this is an equivalent set of hypotheses. Now I want to very briefly talk about Follmann's test. And so what I'm getting ready to show you doesn't really, this notation is different. So this is generically Follmann's test. And then we'll jump back to testing this setting. So here, Follmann introduced a simple test for testing these ordered alternatives. So the mean is 0 versus the mean tends to be positive. The test statistic is we reject the null when our test statistic, and it's some sort of quadratic form, is greater than a cutoff at the 2 alpha level, and that the sum of these components are positive. This is what Follmann developed in 1996. And so we're going to use this test for this. So now let's jump back to this setting and let's develop the theory for this test. So let's let a vector, so xj, be this, and then it's multivariate normal with some mean and covariance matrix sigma times I. So what this represents is that x1 is the first treatment, x2 is the second, all the way up to the kth treatment, and the j represents the observation. So this is an observation from our experiment, but it has each treatment in this vector. So then this mean vector, of course, is the mean of treatment 1 all the way up to mean at treatment k. And since the treatments are independent, that's why the covariances are 0. But we're going to assume there's some sort of common variance between the between the treatments. So let's let xj be the mean vector of these. So you sum them, divide by n, that's what this represents. And we know that the distribution of x bar is multivariate normal with the same mean and actually the same covariance structure divided by n. That's the sample mean. So then if we look at x bar, where we set up these differences, so the first component is 2 minus 1, the second component is 3 minus 2, and all the way to k minus 1. So there's actually k minus 1 components here. And then we set up this matrix where it's minus 1, 1, rest zeros, and then 1 or 0, minus 1, 1, rest zeros. So we set up the C matrix in this, and then when we take this mean vector and C, the product of that, we get this W vector back. Okay. Well then, since these are independent linearly distributed random variables, you know, it's a combination of them, it itself is multivariate normal with mean C mu and sigma squared over n times C transpose. That's the variance of this, right? So now, and of course C transpose is this matrix here. It's 2's down the diagonal and minus 1's in the off diagonal. So under H naught, that all the means are equal. So all these means are equal, which says that these successive differences, you know, if we look at this, are all going to be equal. So it says the mean is 0, and they have the same covariance structure. So W bar is multivariate normal 0, this covariance. Then this quadratic form has a chi-squared distribution, central chi-square with k minus 1 degrees of freedom. Now I have a playlist called Quadratic Forms where we look at this derivation specifically. So next, let's look at the variances. So this deals with the means, right? X1 bar, X2 bar is all coupled in here. Now we're going to look at the means, or the variance, sample variances. So if we look at one sample variance times n minus 1 divided by sigma squared, that a common result is that we know that's a chi-squared with n minus 1 degrees of freedom. Now, since all the sample variances are independent from one another, we can sum them, which is summing chi-squared random variables, and we just add up the degrees of freedom. So this sum is a chi-squared with k times n minus 1 degrees of freedom. And then an unbiased estimate for the common variance would be this right here. You sum all of the variances divided by k times k minus 1. That's an unbiased estimate. Now note that the sample variances and the sample means in the normal setting are independent. That says that this estimate for our variances and our means are independent. So why is that important? Because we know that this is a chi-squared. This chi-squared is independent of the previous chi-squared on the previous page. That says when we take the ratio divided by the respective degrees of freedom, we get an F distribution, F test statistic, so F random variable. So this is the chi-squared divided by its degrees of freedom. And then if we take this divided by its degrees of freedom, which is what this is, because the degrees of freedom is kind of coupled into this right here, then that breaks down to this, right? The sigma squareds cancel. This estimate can be put up in here, k minus 1 and n. That is an F distribution with numerator and denominator degrees of freedom. Well then, so that's our test statistic in quadratic form, right? So then using Follmann's criteria, we're going to reject H naught when this F is too large, okay, right? So if this is large, it says these mean differences are large. So that kind of goes against what the null hypothesis says. But we use the 2 alpha cutoff level, and the sum of these components have to be positive. And that's the Follmann's test for this dose escalation, or a simple ordered alternative hypothesis. Well, my next video is going to be an R program illustrating this. Actually, it's going to illustrate the first one. We're testing treatments against the control arm, and it's going to test this one. So I'm going to call it a dose escalation problem. But really, it's the simple alternative versus a simple tree ordering. Well, that's all I have for today. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.